Okay, looks like it's kind of stabilized here. So good morning to everyone. Unlike the keynote, I'm going to dive into some hardcore code pretty quickly. So this is a talk about Java. So if you're not coding in Java, you might want to grab a coffee and look at one of the other sessions. And it's a talk about Java streams. So if you don't ever write loops, and they're perfectly good programmers who never write loops because they let the database do all the work and just move data from A to B, then you're probably not going to get much out of this either. But if you write loops in Java, then you're in the right place. So in the interest of time, let me skip past the speaker. And my wife, who's listened to my last talk, said, this is really embarrassing. You're bragging about yourself. Cut that stuff out. So let's go right into where we are. So why do people use Java streams? I mean, there was a time when Java 8 came out that most of you are too young to remember, that people used Java streams because it was the cool new thing and you had to use it, but that was a long time ago. Now, the reason that supposedly Java streams came to Java 8 is that they made it really easy to parallelize them. You had your stream pipeline, and it did some computation, and you inserted a dot parallel, and whoa, it was now 8 times as fast because you had 8 cores. I don't know if there are many use cases of this in practice, because not many of us write code that really can load up those 8 cores or whatever many you have. But that was the original use case. When it turned out that really was not that much of a use case, there was some talk of, it could be more efficient. And it could be, right? Because oftentimes we do write code that generates intermediate collections, and that is actually a little bit inefficient. But the real selling point these days is it's declarative. So this example here comes from one of Brian Gutz's papers about this. And so he says, when you look at this code, you immediately know what it does. And you can read through it, and it has something to do with buyers and age and sellers and names. And you can probably figure it out pretty quickly. Whereas if you look at the equivalent loop code, then you actually have to read a line at a time to see what it does. Now, as so many examples out there in blogs by unscrupulous authors like Brian, it's a little bit unfair because he expands, like if you look at the collections.sort, that he doesn't use a lambda, but with sorted he does use method reference, so you could shorten the lower code somewhat, where it would be somewhat more comparable in readability. But still, it's a point to be made. And it's the latter point that I want to dig in more in the talk today and see how valid it actually is. So why don't we always use streams? And so here, as a negative example, I want to cite this this beauty that I got from a collection of solutions to the advent of code problems from last year by Rémi Foix. And so the advent of code is this coding competition every day. There's a part 1 that's pretty easy, and a part 2 that's you're supposed to take your part 1 code and then turn it into something that solves this much more complicated problem. And so he's done all of the part 1s with streams and only streams and nothing else. And so this is the solution to day 22. And as you can see, it would take you a good long time to look at this code and figure out what the heck it does. There's a good reason why he never attempted to do the part 2, because probably he himself couldn't understand his part 1 code well enough to transform it into part 2. So that's kind of the upper limit as to where streams should probably not go. So what about performance? So if you benchmark stream versus loops, and then bring up performance right from the bat, because the first argument that people use for never ever attempting anything with streams, they say, well, surely streams must perform poorly. There's a lot of machinery that goes on under the hood to coordinate the various parts of the stream pipeline, and that must surely cost a lot. And so that was actually my intuition at the outset too. And so for the longest time, I would write a chapter dutifully in my core Java book about streams, and would explain how it all goes, and then I would go back to writing loops, because I figured loops are obviously much faster. And so if you benchmark it, so here is some example benchmark where here you have a loop, and here you have the equivalent stream. Then you'll find out that, so here is the timing for a collection in loops. Here's for the stream, and oh, streams are twice as fast. That can't actually be, right? And so if you carefully look at it, you will find that over here, I have a list, and I pour it into an array list, whereas over here, I have the same list, and I turn it into a stream without copying it into another intermediate container. And it is that copying that costs twice as much. If you take that out and take out the unfair part, then the performance from the collection and the streams are what you would expect, that the streams are an itty little bit slower because of that unavoidable overhead. But otherwise, they are on par. And that is generally what you should expect. So there is this minute overhead with streams over using other solutions. But it's not, it may be large enough for you to worry about, but in most cases it just isn't. Most of the data that you shovel around is not that voluminous, and it really is the point of clarity that's the issue for us. So let's explore that with some simple cases. So for as long as I can remember, if I needed to compute the largest element, of course I would not write the loop that I learned 50 years ago in college. I would just look at the library function, and that's collections.max. It's been there in Java since 1.2. It's easy. And so then with the stream version, when I first saw it, I said, well, that's ridiculous. It's 20% more characters. Have they never heard of the global pixel shortage? And so intuitively, when I saw the dot stream, I would say, that's if there's a library function, just use the existing library function. But actually, if you think about it, the stream version has one advantage. So notice that how here you have to call or else. Well, why do you have to call or else? To deal with the case that the collection might be empty, and then the max is not defined. The classic version throws an exception in that case, because it can't compute the max. The stream version is just better behaved. Okay, so, and once you take that into account, because otherwise you might have to deal with the exception, the stream version is really no worse, and it is just about as easy to read. The second thing is, what if I want to sort an array? Not a list, but an array. Collections lets me down. There is no version in all of Java that gets me the max of an array, except when I use streams. With streams, I just use stream off of my array, and it's the same thing. So in 2024, I've decided I'll just always use max and min with streams instead of with collections, because A, it's more universal, B, it handles that other case. And so I just now internalize that and say that's now my weapon of choice. And I live with the fact that I have to put dot stream, whatever. And actually, then when you go on to look at other things that you often need to do, you need to find something, and you have a list, and you find it with index off. What's wrong with that? But index off, of course, only works if you want to compare with equals. If you have an element, and now you want to see, is there another element that's equal to it in that list? And if so, you get the index. But what if you want to have a more general criterion? Then you have a kind of a messy loop, actually. So I sometimes teach beginning programmers, and I actually wrote a college book about Intro to Computer Science with Java, and there I gave them patterns for common loops, because with students, you can tell them what the definition of a loop is, but it doesn't do them any good if they have to put it in practice. But what does help is if you give them a pattern for the 10 most common loops, and then they apply them pretty quickly. This is the pattern from my textbook on how to find something in a list. And you see, it is obviously a little bit messy, because maybe the thing was never in there, and then you have to make sure that if it was in there, that you jump out when the index is still in the right place. You've written this kind of loop 1,000 times, and you know the kind of things that you need to pay attention to. And here is where streams are actually a big win. So but then, if you know how to deal with optionals, then you know how to deal with that possibility of failure. So that's actually, obviously, it's shorter, and it's super easy to read, right? You see what it is that you're doing. You might say, well, I don't actually want to have the entire collection filtered. I just want to have a first match. But that's what streams give you. Streams are processed lazily. So once the first match is found, the rest of the stream is never investigated. It short circuits and your result comes. So that's actually really nice. Also, the next thing then, if you want to count the matches, there's a loop that you know how to write where you put a count plus plus, but it's the exact same loop except with a count here on a non-loop. It's the exact same stream. And if you want to collect them, again, you don't have to set up something to collect. You just call toList, and there you get them collected. So at this point here, I've decided that I will just stop writing these loops, even though my fingers know them by hand. I'll just use them with streams, and that way it's mentally more efficient. And it's also more efficient when you read them. When you read count, you see that there's counting, and whereas otherwise you have to look for that telltale count plus plus and make sure that was initialized with 0 somewhere. So this kind of simple situation, I think in 2024, we should all be using streams and not get excited about the fact that the dot stream means that's some inherent overhead. If you really care about that small percentage of overhead, that's something to worry about. But in general, I think we can agree one doesn't. Another reason to use streams is the following. So let me again use as an example something from the last advent of code to make it a little bit more realistic, or as realistic as these problems go, right? So in this exercise, you were given some lines of input, and you had to form the number that's made out of the first and the last digit in each of the rows of input for whatever advent of code reasons. And so I wrote this as a classic loop, of course with regular expressions, because when you have a problem, you should always use regular expressions, so that now you have two problems. That's just how the loop looks like. And you look through it, and it starts looking a little messy, and you have to look through some of the finer points here and see what you're really doing. But it's just what one does. Now, then I thought about it when I saw Rémi's solution, and I said, can I do better with streams? And the answer is, of course I can, because with streams, a lot of the kind of complexity just becomes easier. I can call files as lines. It gives me streams of lines. Then I map that by this matcher. I now get a stream of match objects. Then I filter only the matching ones. And then I fish out from the match object, I filter out the groups and put it together, and then I sum them all up. And you've got to agree, that one is nicer. And the reason I think it's nicer, that when you look at this thing, is you say, well, there's really nothing going on there. This is just boring, kind of simple code. There's no excitement, there's no special case that I need to worry about. So it's the, where the policeman says, move along, nothing to see here. And that is what you get. That's the visual signal that you get out of code like that. Whereas when you see code like that, you have to actually look at it to see, is there something to see there? Is this plain old boring stuff, or is there some hidden trap? Because there's enough noise there that you instinctively know, I better try to figure out what this thing does. So that's the other reason that this declarative what, not how code actually has an advantage in daily life where the streams do really make a lot of sense. All right. So one thing in the preceding example is you can make it look even a little nicer, or at least a little more concise, by using these method expressions. So it was lines.streams, and then previously it said line is mapped to p.matcher of line, and you can actually write that thing down as p::matcher. And I must say, when I read people's code, when they do that, I always find that very nifty, because it looks short and sweet. But somehow I always also particularly this version with the p::, to me always looks a little bit magical, and I have to look at this cheat sheet that's out of core Java that that shows the 3 different variants of how you can do this this method expression syntax. Because there's 3 different cases. Here we have a static method. Here we have an instant method. And they look the same in the method expression, but you have to know that they're really quite different things. And then you have the one where you have an object here, not a class, and it's also an instant method. And it also, I mean, again, it means something different. And conversely, when I have one of these things, because I always started writing this, I'm not smart enough to actually figure out the method expression at first, except in a few cases when I've done it so often now that I know it by routine. But I always started with this thing, and then I have to figure out, how to translate that into a method expression. And most of them, fairly straightforward, but once in a while I run into one of these things, and then I actually ask myself, could I make this into a method expression? And then I have to realize, no, I'm out of luck because it doesn't fit any of these three shapes. And okay, but still, it's worth it, I think, because the method expressions, they're easy to read, they're short, and they again signal this is kind of the normal case, because as it happens, or maybe not as it happens, many of the methods in APIs that work with streams have been purposefully set up in such a way that that the method expression is the best shape for whatever the function object is that you put in there. So the verdict is, use them, and maybe you can do this more rapidly than I can. But if not, I think there's no shame in saying write it out as a regular lambda first, and then when you see a real simple lambda, eyeball it and ask yourself, could I rewrite this as a method expression? I think it's worth that effort. All right, so I got kind of interested in this because this discussion I had with Remy, and then a few weeks later I saw that Oracle has a bunch of tutorials on a site called dev.java for beginning programmers, and one of them was written by Venkat Subramanian, this fantastic speaker who doesn't have any slides, and he just talks and codes at the same time, so he had this a series of blog articles in there that said how to rewrite your code to be functional. And so it starts out with this loop. This is his loop. I would never write a loop like that. And so then he says, we can rewrite this in a functional style by using instream.range followed by for each. And of course you can, right? It's the same thing. And it loops over, I goes from 0 to 5, and then it does something. And then he says, well, but what if you have, oops, I missed up the slide. There should be a plus equals 3 here. What if you have a plus equals 3 here? Then he says, well, then range doesn't work, but you can use instream.iterate and generate the loop that way. So sorry, just again, like imagine that I had a 15 here and a plus equals 3 here. That's the copy and paste there. And so he says, with these more complicated loops, just use iterate and for each. And when I looked at that, I said, that sounds a little implausible. Of course, I can make any pattern with iterate. It's this very general construct, but it doesn't parallelize, of course. And I had never really used before, and I had an instinctive dislike for this. It doesn't get any better with a nested loop. So here is your typical loop with i's and j's, and yes, you can rewrite it, and it looks like this. And so why did I not like it? Because normally when Venkat does something, I think he's right. I didn't think it was any easier to read. Maybe it's, of course, because our eyes are so used to these for loops. We've seen them for years and years. But more importantly, when you actually try to do this in anger, what almost always happens is that you don't want to call system.out.println in the loop. I don't write that many loops that have system.out.println, but they normally want to do something, and more often than not, they want to mutate some variable. Well, in a for loop, of course, you can change variables from the outer scope just fine. But if you have a lambda expression, you're not allowed to do, this lambda expression here, you're not allowed to mutate a local variable from the outer scope, because all you can touch is the things that are implicitly final. And is it functional? I mean, I don't think that for each is very functional. For each will have a side effect inside it. And so you can't even say, that you're a better person for using it, right? So my verdict is to avoid for each unless you have a really strong reason that you must do so. And I'll give you one in a minute. So another thing that surprises me a little bit every time that I see a new version of Java. And I get to see a lot of new versions of Java because that's what I do, is that a lot of times it used to be then when an API gave you a result, you got the result as an array. Why as an array? Because 20 years ago, the API designer said the array is the only fundamental structure. A list is something made by man, and maybe you don't like lists, and so we give it to you as an array. But of course, giving something as an array has a big cost. That means you have to pre-size the array, or you have to post-size it and copy things around. And so these days, there's a lot of API that gives you a stream instead. So I'll give you a few examples, and I'd be interested in knowing if you know all of these. So string.lines, files.lines, HTTP response body handler of lines gives you a stream of lines, a stream of strings. Scanner tokens, pattern splitter stream gives you a stream of tokens. So when you have a regular expression, you want to break it up, you can use one of those. If you want to match something in a regular expression, you can use match results or scanner find all, and it gives you a stream, not an array or not a list, a stream of matches. If you call files.list or files.walk or files.find in the really marvelous NIO files library, you get a stream of files. If you want to deal with processes, which I don't do very much, but you get a stream of them. You can get a stream of dates. Local dates until gives you a stream of dates. You can nowadays easily get streams of random numbers. Of course, you could just get just a random number generator and get one random number at a time, but now there's a stream. If you have a string and you want to know what are the code points, or if you live in the last century, what are the character codes in it, you get the result as a stream, which sounds actually kind of strange. And there's a few others that I just dug out where you get stream results. Now, why do they do that? Well, they don't necessarily want to give you a collection back because they figure it might be heavyweight, or you might not want to be tied to a Java util, although these days it's probably a bad argument. It used to be sometimes in the old days they would give you an iterator, but that's also kind of tedious, right? And so a really good reason to give you a stream is here with the files API, where you may not actually, there may be a very large number of matches, and you may only care about the first 10 or so. And so it's an easy way of giving you something that's lazy. If they've populated a list, and you only looked at the first few, then that's a waste. And this way, it's lazily evaluated, so a stream is particularly handy. But it does really then nudge you into the stream API. You could always dump it into a list, but you're probably now at the point where you say, oh, maybe I should actually run with this and work with these as stream. If you don't, if you hate it, because call to list or get the first n and put those into a list, you still have that option, but you're much more likely at this point to say, well, since I already have a stream, and I no longer have to call that uncyclic.stream, then I might as well embrace the stream methods. And this is the one situation where I've actually found myself using for each, because, hey, I had a stream and I had to do something, and I said, whatever. So, moving on. Another example here from Advent of Code. For some reason, we're supposed to find games, whatever that means, that have at most 12 red, 13 green, and 14 blue of whatever. And so you read these lines. And so here was Remy's a very ingenious solution to do that. And in the interest of time and lack of coffee, I think I don't really want to go into the details. But if you look at this hard for 15 minutes, you can figure out why it works. It literally took me this long because he has a nasty trick with the regexes that actually makes this code. I tried to write it compactly, and I didn't because I didn't use that regex trick. So you can have a look at it. But I think we can all agree that it seems kind of unreadable. And the reason for this is that if you look at it, you have a map to int here, and then inside here you have another nested stream. And so generally my feeling is when you find yourself with these multiple nested lambdas, then that is probably a reason that things should be simplified. And also if you find yourself writing a loop inside a lambda, that's probably also a good reason to go back and say, can I simplify that? And the weapon of choice here is, well, before, I said it's hard to read. The other thing that I find when I do this is I get it wrong. I'm not as smart as Remy, so I started out, I have some obvious silly error, except it's not so obvious, and then I fire up the debugger, and to debug through these things is not always fun. IntelliJ tries to make it somewhat easier, but still, it is seriously harder to debug these things than if you have an iterative solution. And so the first thing is use named methods. Well, see if I can get some more space here. Yes. So use named methods. So here I name this method, and then I call sum, so that makes it easier. And the other thing is, can't you break it up into smaller pieces? In this case here, it was pretty easy to do that. I said, let's first filter out the ones that are possible in the sense of this game, and then I do, then I map to the actual integers, and then I sum it. And when you look at the last thing, hey, there you see that streams are a win. Right now, this code kind of speaks for itself, and it actually says what is done, and it motivates why you actually want to look at these other little helper methods. So that I found myself doing a lot when trying to force myself to write things more in streams, just to see how it goes. But once I had these, once I said, oh, this gives me a clue what helper methods might be useful, then I would extract them, write them as helper methods, and then the code became really nice and clean, and I thought that was worth the effort. Yeah, so this is where the image generator, I tried to get an image of nested streams, and this is the absolute best that I could get. So the nested so overwhelms it. I said before, if you have a stream inside a stream, that's a sign of trouble. I want to relativize that a little bit. So over here, I have a very, well, not a very common case, but a possibly common case. There is an optional actually has a method called stream, because an optional is either it's empty or it has something in it. And if you say dot stream, it turns into like a mini stream that's either completely empty or has a single element in there for a single reason, so that you can use it with flat map. So here I'm looking at all of the processes, then I'm calling p.info, which gives me some structure about the process, .command line, and that thing gives me an optional command line if it's known, or it gives me an empty stream if not. If I now do a dot stream and then do a flat map, that automatically skips all of the empty ones. So if you're ever in a situation where you want to skip all empties from an optional, that's actually easy with streams, as long as you know this idiom. The first time that you look at it, you probably take a couple of minutes to absorb it, but once you have it, I found myself using that ever so often and say, oh yeah, that's the old skip the empty optionals trick. And it just looks a little funny with this dot stream and the flat map. But I think that's innocuous. Like I said, it sometimes does happen that you have a row and column structure, and where I feel it's a bit at the outer limit of what you want to do with streams, but in advent of code, where it's often kind of game things on a 2D array, it happened often enough that I said, okay, I'll just memorize this. And there's a particular structure where you have a flat map on the outside and a map on the inside, and then that can do the trick. I must confess, I have to look it up every time, and then I say, maybe next time I can actually create it from scratch, and I somehow never can, because there's the stupid box in here that you need, because flat map doesn't exist on int streams, and what have you. So that's kind of the outer limit of idioms of nested streams that I feel. Otherwise, here is another thing from, I don't know whether that was mine or Remy's code. No, I think it was Remy's. I would never use iterate like this. Where I feel, same tips from previous slide, just refactor this thing so that one gets a name for what goes on inside it. Break it into small tasks and do that. Oh, here's another thing. So I proposed this talk sometime last year, and because I was interested in it, and I was talking to Jose Pomar and Maurice Naftalin about it, and then they stole the idea and presented it at Devox. so I looked at their talk and I said, well, that's pretty basic. And then I said, can you look at my slides? And they said, good luck getting through those in 45 minutes, so we'll see how I'm doing with that. So they kind of get to the same idea, except they're a little bit more stream happy than I am. So go and look at that Devox talk. And so one of the examples that they have is the following, where they say, well, here's an example of finding matches, or no, I think the first match. Finding the first match of a word in a line. So you can see they split the line into into some pattern, and then they here they go through all of the elements in the pattern. For some reason, they're only interested in words of length 3. I guess in French that has some significance. And then then they match them up with this index word. What is that? That is this little record up there. And I didn't like it. So this is what I would call an ad hoc record. It's just there for this one purpose. In other languages, you might return a tuple, but Java doesn't have tuples, right? Java only has these nominal types, so they come up with this thing. And so I thought, yeah, a whole new type for this use case. It does happen a lot, because if you have a loop, there's no problem having a bunch of ambient variables that you set. But with a stream, you return a result, and if you want to return more than one piece of information, and if those data that you want to return particularly have different types, like here, an int and a string, then you have to put them somewhere, and so a custom type. So I feel if you make a custom type like that, at least make it generally useful. So you could just parameterize it so that if you have the same device 10 times in your code base, that you only have one new custom type instead of 10 different types. Also, what I often do in this case, I use map.entry as a poor man's pair. It's a part of the standard library. It's just a pair of a key and a value. And it's there. It has an ugly name, but so to me, it's a signal saying, if that just was a pair, then that's what I would be using. It's fine to have these ad hoc records when they're local, when they don't leak out. And so that I do when I have some internal computation where the world at large does not see that I need to have this packaged up result. Sure, then I'll make an ad hoc record, and then it often has a second advantage. That ad hoc record turns out to be a good spot where you can attach some other helper functions. And I told you, helper functions are what you often want to demystify nested streams. But if it leaks out, like in this case where it's a part of the API, if someone who wants to use split stream as to do work, they're going to have to now use that record. I'm not a fan. By the way, if you have taken the time to read through this code as I was rambling along, you might have said, why are they doing this really complicated stuff with an int stream.range and the split? They could have instead just used a scanner, split along the delimiter, ask for the tokens, and then they get a stream in a much easier way. And indeed they do, but what they don't then get. So this is a much more natural way of breaking up a line with along tokens. What they then don't do is they don't get an integer index, which is what they get with their approach. So hold that thought, because I'll be talking about how to get yourself an index in a minute. So the next thing is there's collectors. Again, the image drawing program couldn't come up with a better image of collectors than those solar collectors on the roof. So this is a part of the Stream API. There's a terminal operation called collect, and the collectors class gives about 40 methods that yield various implementations of collectors. You can also write your own collector, but that's really uncommon. I've only once written my own collector, and that was to prove Jose wrong with one of his puzzlers. So collectors can be easy. Here's a really easy one where I'm collecting. I have a bunch of people. I want to collect those people into a map, and so there's a collectors.map with a map that extracts the key, a map that a function that extracts the value, and that's that. Or that could be completely baffling. I got this one from one of my books. I needed an example for the teeing collector, because in a book you need an example for everything. And, so this was the simplest thing that it could come up. And the next sentence was, you probably don't want to use the teeing collector. Because it's always going to be in a complicated situation like that. You know, I'm sure there's a reason to use it, but I don't think it's a commonly used thing. So it's the same kind of thing. And so when should you use collectors? So there is a very useful and common case when you want to collect to maps. So you have a collection, you've filtered it, you've transformed it in some way, and now it naturally should be poured into a map. And so there is a collector to map. And there's a collector grouping by. What to map does is, as you've already seen, it has an extractor for a key and an extractor for a value. Grouping by has only an extractor for the key, and the value is the object itself. So this one here gives you a map where the name is the key, and the value of the key is the list of all matching people, because there could be more than one person with the same name. So those are the two collectors that I really use the most commonly. Oh, again, by the way, if you do use collectors, do yourself a favor and statically import Java util stream collectors. That way you don't have to put collectors dot in front of everything. It makes it easier to read. Somehow people don't really love static imports, but I think this one is perfectly safe. There's a few static imports that I think one should not be afraid of. Also, a very common case is you want to have a map of counts, that you have some objects and you want to know how often each of them occurred. And that's really easy to do with collectors. You do a grouping by, and then the key extractors, everything just gets mapped to itself. You just want to know how often it occurs. And the thing here is what's called the downstream collector, and it passes everything on to this downstream, and it does the counting. It gives you a long that gets incremented once every time. So why do I like it better? Oh, first of all, the true functional programmers among you will know that it's kind of lame to write S arrow S, because, of course, there is in the function interface, there's a function : identity that does the same thing at the cost of 14 more characters. And so I tried that, of course, figuring, that's, I'm sure, what the functional crowd would have wanted me to do. And I got this little error here. And so that is one problem with the Stream API. More often than not, when I try my first half-assed thing, I get something like that. And so this is Javanese for something went wrong. Right? Because when you try to understand it, it is really difficult to match that up with the actual cause of error. Does anyone see what I did wrong when I put function identity instead of S arrow S? I didn't either until I got another cup of coffee. I forgot the parentheses. Yeah. So, at any rate, I digressed here. When you look at this thing here, what is the classic way of doing it? Well, the classic way of doing it is that you actually manually put in a 0 when you find the thing for the first time, and then you increment what was in there. And that's tedious. So there is a semi-classic way of doing it, and that's by using counts.merge. And so this will very elegantly work. But I can't remember that one either. I have to look it up in core Java every single time that I want to do this. And so I find that here the collect version is clear. It's easy to read. You don't have to understand the magic of how this merge thing works, which was, of course, exactly optimized for this. The other thing is if you want to have a map that of sets, that's what I often want to do, then that's a little bit tedious, but it still works with collecting. I say, this is my key extractor. This is the thing that I want to collect in a set, and then you have this downstream collector that has put it in a tree set. I could use toSet, but then I get a hash set. Just wanting to show what the possibilities are. So these kind of maps I routinely nowadays do with collectors, and I think that's fine. Yeah. Oh, and the classic solution here, by the way, there is a classic solution for collecting to sets, and it works with compute if absent. And again, I know that it exists, but I have to look it up every time. So I find that here the collectors have the definite advantage that once you remember that you should use collectors, you're probably driven to the right solution. Whereas if you use the classic maps, you just kind of have to remember that there was merge and that there was compute if absent and when to use what. And I found that as a slight drawback. Anyway, the latest thing is gatherers. So they were introduced just recently, and there's a few built-in gatherers. There's one that makes windows of fixed size, as that you can see here, one that makes windows of sliding size. If you just look at them, you see what they are. The reason you would use those is if you need to do something with adjacent elements. That was really hard to do before, and now it's pretty easy. Skip, scan, and fold. You're probably not going to be using them. And there's a useful map concurrent that might come in handy. And you can also build your own. Here I'm building one that does a zip with index that would solve the problem from the previous slides pretty nicely. And so the verdict are, they're nice, but there's only a few gatherers that you're likely to need. The sliding ones are good. You'll find zip and zip with index from some other places, unfortunately not in the standard API. They're definitely worth looking at. Checked exceptions are always a problem. So here is a cautionary tale. Heinz Kabutz gave me this, I read through his newsletter, I looked at this article, and I said, Heinz, don't you know that file visitor or walk file tree, that's from Java 8, and you should no longer be using it. You should instead be using files.walk. And he came back to me and said, like this. And because files.walk is actually kind of nicer, it's more consistent, but because of the checked exception stuff, you have to put in all the lines that are put in here in gray, and that is really unpleasant. So that is one of the reasons that streams are not all that wonderful. Anytime you have a checked exception in the Lambda, what are you going to do, right? The Lambdas are not leaking any checked exceptions. And so the standard advice is to use a helper method and catch it in there. There is a thing in Apache Commons that eats up checked exceptions. There's one in Lombok that does the same. I've written a gatherer that does kind of the same thing. So if you have like a fairly short amount of code, like in a script or something, I feel all's fair in love and war. And somehow squelch those checked exceptions. Of course, for real production code, that may be different. Anyway, so I now see that Jose was right, that I'm going to have to just race through the last slide here. But I do want to say this because there's one good thing in there. So if you actually want to parallelize, then streams are definitely your friend. With a simple .parallel or .parallel stream, you get better performance. So they split, and they work fine. So you should expect an n-fold speed up where n is the number of your processors. It doesn't work for tasks that mostly block. Heinz Kabutz told me that he has made a good amount of consulting revenue at one point when streams first came out by telling people exactly that they should not be just running blocking tasks in the fork join call. And so could you use virtual threads? You can't with the fork join pool. It does not work. And that's where the gatherers have one other trick up their sleeve. And that one, I've seen some blog said, this is probably the best thing in Java 22 or 23, I think, when it came out. And that, that could be, where if you want to do a bunch of blocking operations concurrently, then this gatherer map concurrent does exactly what you want. So you can do whatever blocking work over a data structure, over a range of data. And it does, it works very nicely if somehow this thing fails, it shuts down all of the other tasks. So if you ever think of, gosh, I have the stream, I would like to have its work done somehow concurrently, but these tasks are blocking, then go and check out Gather a Map Concurrent. It really is nice. So I obviously will not have time to give this demo, but I'll give you the upshot of this demo. So the upshot is I've tried all of these rules out on something that I've taught a long time ago when I was teaching Scala, and I dimly remember. And I said, okay, I'm going to take the Scala thing and, without actually looking at the Scala code, rewrite it in Java. And I did it using, by the way, as a shout-out to Sven Reimer's project, this thing called JTaquino. It's a notebook. It's a Jupyter-like notebook that's written for Java in Java. And so here you see me struggling through some of these things. And the sad thing is, when I try to do this, the temptation of nesting these streams was irresistible. I said, oh, I can just push this along just a little bit longer. And so I felt in the end the solution was kind of ingenious. It was actually shorter than the Scala solution, to my surprise. But it was also, I felt, even though my best efforts of breaking it up into 10 subtasks, it was still not broken up enough, and it would need one other round of refactoring. All right. And it was not fun to stare at the compiler errors in the process, because every time I made some dumb typo, it was just not good. Yeah. Anyway, so yeah. So just to summarize, so don't worry about performance. Unless you do something wasteful, the performance is likely going to be within 10%. Streams can make code nicer to read, particularly for short, standard, simple things that the stream library absolutely supports. So here's some good use cases: max, min, sorting, sums, averages, finding, counting, collecting matches. Method expressions are nice. You should use them. Complex lambdas are not nice. It's surprising after a bit of practice with it how easily they roll off your fingers. Then budget in the time to refactor so that people later can read the code. Also, if you find that things aren't so nice because you get weird errors, that's a good time to get a cup of coffee, walk around the block, and then redo it with some helper methods. Because otherwise, you can spend a good amount of time trying to stare at these compiler errors. And right now there's a flurry of blogs and talks about this stuff that all exhort you to be more functional. Functional is not pixie dust. You don't just sprinkle it over your code. Don't turn every loop into a stream. It really does require some amount of judgment. Yeah, checked exceptions are a pain, and so you should think about your remedies and know when you're willing to apply what or just not do it. Like I said, collecting into maps I found was a win. And that means you don't just need to know the stream API, but also these collectors. And there are, every time that you get, like you read the sections in my book about this, it says here the collectors, and then it goes on this rabbit hole of downstream collectors and shows you 40 different, because there are 40 methods, 40 different ways of doing this. Most of them are not actually useful in practice. It's kind of amazing that you can do it, but you shouldn't. These gatherers that just came out, there's a handful of useful ones, and I expect a couple more will eventually materialize in the standard. And most importantly, once you do get started and you get bitten by the stream bug, just budget some time for refactoring, because there will be the point when you find it perfectly logical and easy to read, but I guarantee your peers will not until you do that refactoring. And the end result is, of course, that you have code that is clearer to read, and that's what we're aiming for with this particular little thing. Code that is easy to read and easier to maintain. And that should be the major motivation for most of us to use streams. Okay, thank you.